Maxwell. So, we're going to talk about James Clerk Maxwell in this video. Who is James Clerk Maxwell? What influence did he have on the history of science? And what can we teach students today? My name is Amos Tarfa. I'm a medical physicist. And the man James Clerk Maxwell plays a very special role in the field that gave rise to what medical physicists do. Part of what inspired this tonight, now I have a lot of books about Maxwell, but what inspired it tonight is a book on the elements I'm reading. It's talking about different elements that were discovered through history, and it gets to this section called the Radiant Age. And in the Radiant Age, it brings up Clerk Maxwell and his work in the 1860s. Before I go on, I want to share briefly that I have written a book series or a journal series called Counting to Calculus. It starts by teaching people the fundamentals of math. Is like sketching a rocket, and then you get the rocket in place, it blasts off, and then it goes off into space. Now, I don't plan to go to space, but I'm just showing you a resource. This is the algebra resource, and it has a section on chemistry, and it's called Algebra 1, Everything Algebra 1 and Algebra 2 with Chemistry. That's the subtitle. And the idea of this is that I want people to learn chemistry along the way as they do algebra. And one of the most important aspects of chemistry is the elements, right? Understanding the elements and people behind the elements. Now, one thing you can do is you can use these workbooks, which you can find on Amazon, as a guide for any math course or any textbook you're using, because at the end of the book, I give you resources like a reference guide at the end of the book. But let's talk about James Clerk Maxwell in more detail. When someone asked Albert Einstein, this is a book called Einstein's Greatest Mistake, which is not, it doesn't go into detail about Maxwell. But when someone asked Einstein, do you stand on the shoulders of giants like Newton? Einstein actually said, I stand on the shoulders of Maxwell. So who is this Maxwell guy? Well, Maxwell, if we're going to discuss Maxwell, it is best to probably discuss it in the context of Maxwell and Faraday. Maxwell did work in electricity and magnetism, some of which was influenced by the work of Michael Faraday. So let's read a little bit about Maxwell, and then we'll go from there. It says, light had always been a contested affair. For Isaac Newton in the late 17th century, it was composed of a stream of particles, whereas his rival, Robert Hooke, insisted that light was a wave. Nothing, Hooke wrote in 1672, but a pulse of motion propagated through an homogeneous, uniform, and transparent medium. Antoine Lavoisier included light in his list of elements in 1789 without specifying its nature, but Hooke's view prevailed. In the early 1800s, the English polymath Thomas Young demonstrated how light rays passing through two narrowly spaced slits interfere with one another to cause a pattern of bright and dark bands, a phenomena that seems to demand a wave particle of light, a wave picture of light. But waves must have some medium to carry them, as Hooke said, and the ether, as they used to call it, was resurrected to serve that role. It was thought to pervade the universe, invisible and too tenuous to measure or weigh. In the 1860s, the Scottish scientist James Clerk Maxwell explained how this worked. He showed that disturbances in electric and magnetic fields travel through space at the speed of light, and supposed that this, in fact, what light is: an electromagnetic vibration propagating through the etheric medium that supports these fields, just like sound waves traveling through air. It was this ether that bears light across the vacuum of space. The vast interplanetary and interstellar regions, Maxwell wrote, will no longer be regarded as waste spaces or waste places in the universe. We shall find them to be already full of this wonderful medium which extends unbroken from star to star. Maxwell formulated a set of equations to describe these electromagnetic waves. It was immediately clear, however, that the theory didn't impose any limit on the wavelengths and the frequencies of the waves. The wavelengths of visible light could be measured and fell between, in today's units, 400 billionths of a meter for violet light and 700 billionths for red light. But the wavelengths of the electromagnetic vibrations could in theory be longer and shorter than this range. Long wavelength vibrations were first detected in 1887 by the German physicist Heinrich Hertz. The unit for frequency is Hertz, and now we see where that comes from. But Hertz's work was inspired partly by Maxwell's work, who came before him. They were later called just radio waves. Just 9 years later, Italian inventor Guglielmo Marconi showed that the long reach of radio waves could be used for transmitting messages over great distances. broadcast from a source of such waves to a device that could detect them. In 1892, the English chemist William Crookes wrote that radio waves could be used for telegraphy without wires, posts, cables, or any of our present-day costly appliances. A few decades earlier, a telegraph cable had been laid with great expense and difficulty across the Atlantic seafloor, but now messages could be simply sent, literally, most scientists believed, through the ether. In 1901, Marconi broadcast at a radio signal from Cornwall in Western England to Newfoundland in Canada. Electromagnetic waves could also have wavelengths shorter than those of visible light. Ultraviolet light, just beyond the violet end of the spectrum, had been known since 1801, when the German scientist Johann Wilhelm Reiter found that this invisible form of light separated out with a prism could trigger the darkening of silver salts, just as normal light does. The story gets very interesting as we go on. A few decades later, this process was used as the basis of photography. By the way, Maxwell also gave us the first color photograph. He was born in Scotland, and you could go to his house in Edinburgh, actually, where it's now a museum, and you can see different aspects. Very, very cool stuff. We went back in 2023, and God willing, I hope to go back, take some people with me to show them around Edinburgh. So stay tuned for that information. So it was disputed for a time whether the ultraviolet radiation was of the same nature as ordinary light at all, but Maxwell's theory helped to rationalize it. In 1895, a German physicist by the name of Wilhelm Röntgen discovered another kind of invisible radiation that could also darken photographic emulsion. He called them X-rays, and they turned out to be the electromagnetic vibrations with wavelengths hundreds of times shorter than those of visible light. By the end of the 19th century, it seemed like the world was pervaded with invisible rays, many of them revealed by photography. Some of these emanations proved a figment of the imagination, such as the N-rays postulated in 1903 by a French physicist, Prosper René Blondlot. Others, like the mysterious uranic rays found to come out of uranium salts. And you will find that in 1896, radioactivity was discovered by Henri Becquerel and the work of the Curies, the Marie Curie, Pierre Curie, Henri Becquerel. So by the 1903, we have, it says that the N-rays postulated in 1903 by the French physicist Prosper René Blondlot. Others, like the mysterious uranic rays found to come out of uranium salts or cosmic rays streaming from space, presaged important discoveries in the early 20th century science. For some scientists, these rays helped quasi-miraculous properties or held quasi-miraculous properties. Crookes argued that Maxwell's ether might carry messages not just over the Atlantic, but also between our world and the spirit plane, channeled by another kind of medium, the spiritualist who held senses to communicate with the dead. In the radiant world of the 19th century, anything seemed possible. Now, that last part, of course, is not it's not something that that carries any weight there. But imagine now we're moving into a world where people are learning about the unseen rays, like you don't see X-rays with your eyes, right? But I work with X-rays. I work with radio waves in MRI and X-rays in CT and radiography. You don't see these things with your eyes. We can detect them. We can study them, right? And so it's really interesting. Now, one thing you might not know about Maxwell is that Maxwell was actually a man of faith. He was a Christian, and he took his faith very seriously. If you look at the door of the Cavendish Laboratory, you will actually see that he quotes a book in Psalms and talks about wonderful are the works of the Lord. There's a great paper here that I will be presenting on our channel, The Genius and Faith of Faraday and Maxwell. We'll be talking about that in more detail. But Maxwell is a key figure in physics, but he also did have an impact in certain elements of chemistry. If you're in a traditional chemistry classroom, you're going to learn about light, Planck's constant, and some of that goes back to the work of Clerk Maxwell, or James Clerk Maxwell, as Professor John Lennox calls him. I'll leave you with one book. It's called Can Science Explain Everything by John Lennox. And you'll realize that one of the things that made people like Maxwell exceptional is their ability to understand the relationship between science and philosophy and reasoning and logic. They were very different back in the day. The world needs more people like Maxwell. So I'm going to keep enjoying my book on the elements, but stay tuned for more videos that go with our chemistry class and our algebra concepts from the Counting to Calculus series. I look forward to seeing you. Feel free to subscribe for more videos like this. Take care and have a blessed day.